Good morning. Today we're going to talk about section 3.3 entitled Measures of Variation. And to begin, I want to cite a homework problem from the previous section 3.2. In particular, the listing of Jefferson Valley Bank waiting times versus the Providence Bank waiting times. As you may recall, Jefferson Valley had a single line sorting out to individual tellers, and the Providence Bank had individual lines for each particular teller. All right, if we look overall at these two data sets, we can measure the center of each data set, and it turns out they're all the same. The mean for both sets is 7.15 minutes. The median is 7.2 minutes. The mode is 7.7 minutes again for both sets, and the mid-range for both sets is 7.1 minutes. So even though these two data sets have identical measures of center for all four of our measures of center, we can see that the behavior of the data is very different. In particular, the Providence Bank certainly has more variation. Certainly these numbers here are more spread out from the measures of center than the Jefferson Valley Bank. So let me write that down here. I'll say more variation, or more informally, more spread. Data is spread out more. Alright, so the motivation here is we need not just a measure of center, we need a measure of spread. We need a numerical measure of spread or variation. And that's what we're going to talk about today. Just as we had four measures of center in the last section, we're going to have three measures of variation for any given data set. All right, three measures of variation, and the first one we're going to talk about here is range. Not mid-range, but range. Right? Your range is nothing more than your maximum value minus your minimum value. That's all it is. And of course, this is a crude measure of spread, as you can clearly see, and it is very vulnerable to fluke values that may not give a true indicator of what's going on in the data. So for this reason, range is typically not used very much. It is used sometimes when your data is reasonably well behaved, and the big advantage of range is that it's quick and easy to compute. Next one we're going to talk about is standard deviation. Well, your standard deviation, it measures what I'll call the average deviation from the mean for all your different data points. All right, now there is a formula for the standard deviation. I'm going to copy it down here. Now the first thing I'll say, well, we're going to define this in terms of a sample standard deviation. There is an analogous population standard deviation that typically is unknown and unknowable. The sample standard deviation, the generally accepted symbol is a small s. Okay. All right, now let me build up the formula for you here. It kind of involves a rather large root expression. I'll take x, which represents all my different data values, a variable that represents all different data values. From each data value, you will subtract the sample mean. Alright, so to compute your standard deviation, the first thing you need to do is compute the mean. Right. Take those differences from the mean and square them. Add up those squares. Divide by little n minus 1, your sample size minus 1, and then take the square root of this entire expression. Alright, that is your sample standard deviation. Alright, some notes about the sample standard deviation. Well, because square roots are always positive or 0, your sample standard deviation will always be positive or 0. Make a bulleted list here. The larger your value of S, that means the larger average deviation from mean, right? Remember, your standard deviation is your average deviation from mean. So a larger S means more spread of data. And of course, a smaller S, smaller value, means less spread. Okay? The units of S are the same as the units of the data. And if your units of your data is in minutes or seconds or kilograms or whatever, then the units of S is the same. Alright, I want to give you an example how to compute S. Right here, let me write this down. I'll say computing sample standard deviation by hand. Well, by hand I mean we are going to use the calculator, but not in statistics mode. And let me give you a simple example here. Let's say I've got this from the cookie, chocolate chip cookie data. Let's take a small subsample of that data. All right. And let's say we want to compute the standard deviation for this data. Now, remember, the first thing you need to do when you compute S is to compute the sample mean. So the first thing we'll need is the sample mean, and I've got that computed as 23.5. Alright, what I'm going to do here is make a table. Call this the table method for computing standard deviation. I'll make a table with 3 columns. I'll have an X column, an X minus X bar column, and an X minus X bar squared column. Alright, notice the numerator of this fraction under that root sign is going to be the sum of this third column. Alright, so that's where we're headed in this table, is to get a value for the sum of that third column. Alright, I've got 4 values of data, so let me write them in the data column. Alright, X minus X bar, well, X bar is 23.5, so if I take 22 and subtract 23.5, I'll get a negative 1.5. And I'll fill in this X minus X bar column. For each value of X, I subtract 23.5. There's a 24 there, the last row. Now I square each of these values. And if I add up now this third column, the difference from mean squared, I get 11, a whole number 11. Alright, so that 11 is going to get tucked in the numerator of that root expression for sample standard deviation. Alright, let me go down and get some more room here, write it down here. So sample standard deviation, you write down the formula again, summation x minus x bar squared divided by n minus 1. Alright, as we've seen, 11 will get substituted in here. Don't forget about the root. And n minus 1, well, it's your sample size minus 1. And we had 4 data points in our sample, so 4 minus 1 is, of course, 3. Alright, so my sample standard deviation is simply the square root of 11 over 3, and that's 1.91. So S is 1.91. Alright, so remember, sample standard deviation gives you an average deviation or average distance from mean. So let me write that down. My average deviation from the mean value of 23.5 chips is indeed 1.91 chips. Right, so when I think standard deviation, in my mind, often I think average deviation or average spread. Right. Our other two measures of spread, well, the range is, of course, the high minus low for this data set. If I look up here in the data set, go back up to the screen, well, oh, hang on a minute, went too far. If I look at my average data set here, or my original data set for this example, the high is 26, the low is 22. So the high minus low is 26 minus 22, and that's, of course, 4. All right, there is a third measure of spread we call variance. Well, your variance is given the symbol s squared. And all it is the square of really the square of the standard deviation. It's your standard deviation formula without the square root. And as you can tell, we've already computed this really on the way to getting the standard deviation. Alright, so my variance for this example, s squared, is going to be 11/3. Which is 3.67. In decimal. Alright, so there are our 3 measures of spread for this very simple chips example. Standard deviation was 1.91. Range was 4. And the variance was 3.67. Variance we won't use very much here, and range we won't use very much. We will use it sometimes, and you will see it on the online exams and the in-class tests. Standard deviation, like the sample mean, is by far the most used measure of spread in common practice. Let me write that down. Standard deviation is by far the most used measure of spread but the others, range and variance, are used sometimes, particularly in more advanced formulas as we go on in the course. Alright, I want to recall the Jefferson Valley example and the Providence Bank example. I won't write down all the numbers again. Certainly you can see them in your book or earlier in this video, number 24 on page 93. We did see that the Providence Valley Bank had more spread and the Jefferson Valley Bank had less spread, less variation in their data, right? Alright, what I'd like to do is compute the standard deviation for the Jefferson Valley Bank. And we'll do it with our table example. It's going to take some ink here, so I'm going to try to be very careful about getting everything in one screen. So let me compute the standard deviation for the Jefferson Valley Bank. Let me get a fresh screen here. Alright. Alright, give me a minute here. I'm going to pause this. Alright, what I've done is made a 3-column table and listed all the values of waiting times for the Jefferson Valley Bank. And I'm going to fill in the columns x minus x bar and x minus x bar squared as I did in the previous example. And then stuff those needed values into the standard deviation formula. Hang on a minute, forgot summation. So S is summation x minus x bar squared divided by little n minus 1. And of course, the first thing we need for this formula is the sample mean. Well, we've already computed that earlier in the class, and we found the sample mean for this Jefferson Valley Bank was 7.15 minutes, right? So what we need is the sum of this third column. So I'm going to go ahead and fill in x minus x bar and x minus x bar squared for each of these data points. Take each data value, I'm doing the best I can freehand here, x minus x bar, subtract 7.15 for each data point. Oops, 0.05. .3, positive 0.15, 7.4, subtracting 7.15 gives me 0.25, and the last three entries in the second column are the same because the data points are the same, positive 0.55, positive 0.55. Alright, so that looks pretty legible to me. Alright, so now I'll go ahead and square each of these values. The first one I already squared. I'm going to use the calculator for this, of course. I don't insist on 10-digit accuracy that your calculator gives on each and every calculation. It's kind of a trade-off, I guess. I always say keep as much accuracy as you can stand until the end of the problem, then you can round off if you like. 0.30. Hang on, 4225, 3025. 1225 0025. Oop, hang on a minute. Let me check it. 4225 3025 2025 1225.0025 .0225. Then the last three entries 0.3025. Okay? Alright, and again, once I've got that 3-column chart filled out, I notice that the numerator of that fraction inside the root sign is the sum of this column, right? So I say summation x minus x bar squared. Well, I get 2.045. Right? The sum of all these values. So that to be a 2.045. Okay? Alright, now I'm ready to sub into the formula, the standard deviation formula. S equals square root of 2.045 divided by little n minus 1. Well, n is 10, and so 10 minus 1 is 9. So my sample standard deviation is going to be the square root of 2.045 over 9, and I will use the calculator to grind that out, and I get 0.48. 0.48 in waiting time minutes. Alright, so a bunch of work there. So let me write this down. The Jefferson Valley standard deviation was S equals 0.48. Alright, now I won't draw it out here, but the Providence Bank standard deviation was 0.57 in minutes. Now you recall earlier in the lecture we noticed the Providence Bank with their individual waiting lines clearly by inspection had more spread of data, and that's confirmed with these values of standard deviation. Since this standard deviation is greater than the Jefferson Valley standard deviation, we can conclude the Providence Bank had more spread or variation in its data. Higher standard deviation, greater spread. Alright, we'll call it a day here for section 3.3, and this concludes section 3.3 online video lecture.